Hello, everyone, and welcome to Handmade Hero Show, where we code a complete game live on stream. We are going to be doing some ray tracing work today. We already know what we're doing because last weekend we stopped at a point where we had a couple things left to implement. I would also mention our Kickstarter is almost done. You can actually see there are like 25 hours left. So by the end of tomorrow's stream, it will be over. And so it's the last chance to get a bunch of these different versions of the comic over here. So if you're interested in that, check it out. You've got exactly 1 day left. Let me just kind of jump back over to what we were doing here. There's a couple different things we actually need to do. It's fairly complicated, this particular scheme, in terms of the number of steps involved, but the actual routine that does the ray casting, which is the part we care about, is very, very simple. And in fact, we already wrote that part. If you take a look at the raycast routine here, grid raycast is the one in question. You can see that you've got a fairly straightforward preamble that's basically the same as the other preamble, but simpler, doesn't have a stack. You can see that it just has a walk index here. It loads from a walk table which grid nodes to do. It then looks in those grid nodes and tests all the leaves in those grid nodes. It's just that one nested loop, and that's it. And after it's done, it goes through and does the work of producing the hit. Oh, it looks like we didn't quite finish this. Actually, it looks like we were still working on how exactly we were going to do the downshift. Yeah, no, we will avoid doing gameplay code for as long as possible. I hate gameplay code. If we can just work on engines for the rest of our lives, we'll be very happy. Gameplay code is for game designers. They do that. I don't like it. Ideally, for me, it's just like, I can work on the engine all the time, and then there's somebody who's a good game designer who comes along and does, whatever the design is. That's their job. Gameplay code is incredibly simple. It's much simpler than, engine code, but design is very hard, and has nothing to do with programming, really. I mean, it does in the sense that you have to be able to program to do it, but you can't really employ programming skills to make good design. It doesn't work that way. Design's a different thing. It's a different skill set. It's like being an artist, right? It's a different skill set. So anyway, in terms of this routine, we definitely have some issues we want to make decisions about now, I guess, because we've written most of it. If I compile it here, you can see there's almost nothing left that's not done. It's just this one piece here where we try to figure out what the normal is. So we've got a couple different ways we can do that. And just to refresh your memory, so coming out of here, when we do this collision detection, or I should say ray intersection, what we're going to have is 4 ray intersection T values. So 4 places the ray intersected boxes. And some of them may be nothing. They might be still at infinity, so the ray didn't hit anything. But either way, we've got 4 of them. And when we get down to here, we want to only process the closest one. Now, if you take a look at this piece of the routine here, what you can see is that actually what we do is we're taking this particular, these 4 lanes, we are converting them down into a thing that we can test using a single instruction called minpos EPU16, which produces whichever the smallest value is amongst the things in the ray. Of the 4 lanes, whichever one's tiniest. And then we have a shuffler that we load from a table that just says, look, if you want to take any of the lane values that you've got, so things like the box min or the box max, we can produce a vector quantity that now has the correct minimum value. So out of the 4 lanes, whichever one's the one that was the closest hit, we can spam that out to all 4. And so we can do that just using a very simple shuffle. You can actually see us doing this P shuff B here with the shuffler. This like picks the R or the G or the B from the ref hit color based on whichever one was the closest hit. Like that's what that does, right? So it's pretty straightforward what we're doing there. The question is just, when do you do it, right? So because of the way that the floating point unit now works, I shouldn't call it the floating point unit because there's two in a Skylake chip, but the way that the ALUs in Skylake work with floating point numbers, actually there's more than two depending on how you want to look at it because there's a divider and stuff, but it doesn't matter. That's not irrelevant. That's not relevant here. The relevant part is simply to say all of the floating point operations that we're going to do are 4 wide. There's no way to do a single floating point operation with some other thing unless you're going to use like the x87 legacy hardware. So really what you're doing in an x64, if you're doing a scalar multiply, is you're still using the 4-lane multiply. You're just letting it know that if it wanted to, it could like save power by not doing that, right? But it's still in the 4-lane. It's still using a register that's 4 wide. So for our purposes, we actually don't ever care if we do 4 multiplies or 1 multiply at the same time because they cost the same to us. The actual runtime penalty to us will be the same. And so it's our decision when we try to move things from 4 wide to single because it doesn't matter. And so we want to pick that point by whatever will give us the best performance, right? Because we can pick it however we want. We unfortunately do have to do it, and the reason is because we don't have any way of looking up into our voxel, because that's a memory operation. SSE, even up through 4, until you get to like AVX 512, doesn't have scatter gather. So you can't go grab multiple memory locations and put them into 4 lanes. That's not an operation we actually have. So by the time we get to voxel compute voxel irradiance at, that actual operation can only happen in scalar. So by the time we get down here, we have to have converted our 4 wide code, which we came out here from, into 1 wide code in order to do compute voxel irradiance. So that's just a requirement because we don't have any way of doing memory ops 4 wide. And so, I don't actually know when that place is, and that's what we need to do here. If you take a look at what I was sketching out in terms of solving for probe sample P or probe sample N, what you can see is we mostly, if you look, we mostly have here a situation where we're trying to produce a normal, but all we actually know about our hit detection is we know where we hit the box. Like, we know the location where we hit the box, and we know like the min and the max of the box and the center of the box and so on, right? So we need to figure out how we're going to produce a normal from that. And one way that I hypothesized we could do it is by doing like a table load, right? So figure out some way to, load out of a table based on some kind of a mask that comes out of, a comparison or who knows what, right? And it's hard to say, like, what would be the easiest way to do that or what would be the best way to do that. And what we were hypothesizing here is that we would do some kind of comparison and produce like a sign mask or a greater than mask. You can see us like doing various things here. Presumably this was an MM comp here. But that's what we need to think about now. And the probe sample P, on the other hand, that's not so interesting either way, because that's an extraction, and we can either do the extraction here or we can do the extraction here. We can do it either way. And so I'm not sure either about that one, but this is like probe sample P single. So in order to do this, we need to, well, I guess I could do it this way. We need to extract 0, like from each of these, right? And we could make something that converts that, like like an extract element kind of a thing that converts that. I don't know if we want to do that or not, but for in fact, if you look here, you can see we're effectively doing that, right? Like this is what we're actually talking about here. So when we do this, and it looks like we've already shuffled our T-ray here. So if you've already shuffled T-ray, then this is going to produce the correct results everywhere. So it itself doesn't need to be shuffled. So probe sample P, if you just extract the individual low components from it, like so, you just have your answer, right? So this is probe sample P single, and at that point we know that really it's just probe sample N that we wouldn't have, right? So you can see here that probe sample N, and this should really be called probe sample N single probably, because it's not a combined value, even though we don't really build a combined value of that. What you can see is the only real sticking point in terms of stuff we don't really know yet is how we would produce this normal. And so we need some way of producing that. Now, if these were spheres, it would be easy because the delta, like if you just subtract the point you hit from the center of the sphere, that's the normal. You just have to normalize it, but it's the correct direction. And if you don't care about normalization, well, then you're completely done. But it's just a normalized operation. That's the only thing you'd have to do. Unfortunately for us, that is not the case, and what we end up with here is a situation where we've hit a box. We know the location on the box we've hit. We know the center. If we subtract the two of those, we actually know that whatever the highest absolute value is, we do know that that is the component of the normal that is filled. Because a box, an axis-aligned bounding box, the normal is just plus or minus 1 in one channel, X, Y, or Z, right? That's it. The rest of the values is 0. That's an axis-aligned bounding box, has normals that are literally just like 1, 0, 0, negative 1, 0, 0, 0, 1, 0, 0, negative 1, 0, 0, 0, 1, 0, 0, negative 1. Those are the normals. That's all they can be. So we're just trying to figure out which one we have. Now, if we were to do, so you look at what happens here, we do a hitbox radius and a hitbox center. One of the interesting things about this is we don't really need the radius. I don't think. Well, we do. So one of the interesting things here is, I guess the reason we have the radius is if we scale by the radius, so for example, if I take the probe sample P and I subtract the hitbox center, and then I scale that using the Hadamard product here, then what I end up with is this scaled D value. That now has inside it the values that would tell me if I took whichever one was maximum, I would know which one was the correct normal at that point, right? The problem is it's absolute value maximum, right? So it's not quite what I want. Now, taking the absolute value maximum actually isn't particularly difficult, and that's why we kind of did this thing here. So let's actually see what would happen. Let's suppose we wanted to do an absolute value of the components of scaled D, right? And so we wanted to just start merging these together. So in order to merge these together, what I would want to do is, because I now know I need to shuffle one of these, right? So I want to shuffle the one of these that's I want to shuffle the values out of this so that I know that I'm only working with the closest hit. And again, I'm not sure in which order I should do this. Like maybe the answer is I should have shuffled these two because that's just 2 shuffles and then everything else works in scalar. Again, it's really hard to say. I'm not sure. It's one of those confusing things. The other thing is we probably want to repack these slightly differently. Like, we kind of want them now to be such that they're interleaved X, Y, Z, which we could actually do probably without much of an issue. So, yeah. I guess maybe after you get to this point, you want to interleave the X, Y, and Z, but you would need to shuffle them down. And the question is just, should you just shuffle these two first? And I think it's better to shuffle after, right? Because if you have to shuffle these two, you're doing 3 shuffles, plus 3 shuffles. So it's 6 shuffles total. And if you just shuffle the output, you're only doing 3 shuffles. So I think you win if you just wait, right? You just wait till the end. On the other hand, this does shuffle. So if you shuffled this... Well, that doesn't shuffle. That's technically an extract. So... I think you shuffle probably at the end. So if you were to do that, right, the scaled D value is just the same thing that we did here. So if I wanted to do a scaled D single, it would just be something like this. And then the question is just like, okay, so if I extract those 3 and then I want to merge them, right, to do comparisons on, then I need to do 2 operations to merge, right? So it seems actually like maybe you wouldn't quite do that. You just do the merge directly. So I guess that tells me something I need to know. We probably would do the merge directly here. So what we would do is say, all right, these are our vectors, right? They need to be shuffled. So that we replicate out the lines, but in addition, we then want to merge them together, probably so they go X, Y, Z, 0, would be my assumption, so that we can then do things like use the mauve mask on them or use the same technique we did here to find out which one is the minimum, for example, or which one is the maximum, things like this. So... how would we do that? The other option is, again, yeah, we use a comparison to compare like XYZ and YZX, and then we use a table for that. So like there, if we knew that like X was less than Y and Y was less than Z or something, you know, and X and Z, we'd have all 3, you know, we'd have comparisons on all 3 pairs of values at that point, X, Y, X, Z, and YZ. And then we should be able to use that. That actually seems pretty good, right? So, yeah, I think what we would want to do maybe is this. I think what we had here was probably right. I think we want to produce like XYZ and YZX, right? And then what we would want to do is just do a comp, right? So, something like this. So that we can get a comp here and we just say, all right, the sign mask is just the packed XYZ. The greater mask is like the, you know, comp. And I guess we could, you know, do it that way. And then we just look those up in the table as we expected. Seems plausible to me. Right? Seems plausible. I mean, is it the best way? Probably not. We can probably get better here if we really want to. And so then what we need to do is we just need to have some way of producing these. We know that we can just shuffle this. So if we have an XYZ, we can just shuffle the XYZ around. So to produce a YZX, it would just be like a 1, 2, 0, right? So we don't really have to think about that very much. We can make that out of this. So this is really the one that's a little bit tricky because we have to merge 3 values. And so for that, we just need to So yeah, again, just trying to think this through a little bit more carefully. When I think about what's going on in there, I'm not sure. Maybe there is an even better way to do it. Because the only thing we need to do, actually, is to knock out the values that are not... The only thing we would need to do is mask out the values that aren't the largest. So actually, if we were to do a comparison on them, we probably wouldn't actually need to use the table because we could just knock out and normalize. So I think actually we don't really need these. I think all we need is one mask, right? So you would do this, you would do like... You would take the absolute value of it, which just ands, this is just an and, right, to get rid of the high bit. You would do the comparison, and then you would just load out a mask, right? You'd just say, like... There'd be some clear mask that you would do, where you would do a mauve mask on the packed... on the comp, and the clear mask table would just have whatever the actual clearing mask is that you actually need. You would then, after loading that in, you would just and it out. So you would say, all right, the packed XYZ equals the packed XYZ and the clear mask. So now you've gotten rid of whatever the components are that aren't the greatest. That aren't the highest component in there. And after you've finished, you just need to normalize that one value. So in order to do that, you just need to divide by 1. In fact, you can just do that first. So you can say packed XYZ equals like 1 over packed XY, times equals 1 over packed XYZ, right? I guess you don't even really need to do that. You really just need the sign bit. So I guess it's really just an or. You just say we have the vector of all ones, right? It's this. So we can just say, hey, it's a vector of all ones, and then we or in the signed bit from whatever the packed thing is, and that's it. Right? It's all ones. We know that we would clear... oops. Trying to think if there's a way to do this. So I'm not sure if there's another way to do this, but I'd have to think about it. We just want all ones. We want to take whatever the original sign was, which is this, and OR it in. So that way we preserve the sign. And then we just clear out whatever the components are we don't want. I think that's it. You don't need this. And you don't really need this. You would just say, look, there's a whatever, so you'd store it. You'd say so you'd have the probe normal single here, and it would be like a V3, but we know there's actually 4 values, so we want to actually write like the whole thing, like so. And then we would just take just the one part of it. I think that's it. So it still feels a little overwrought. I feel like we could do better than this if we put our minds to it, but like roughly this is what we're talking about, right? And we can't quite do this. We need this to be a separate value, right? So the AABB packed XYZ is not the same. Right. But that's basically what we would do. And it bloats it out a little bit much, right? I'm not thrilled about it. Also, I might want to check compute voxel radiance at. I'm not sure what this thing actually does. Here, it's just trying to produce a voxel index and a txty. So we could, again, actually extract just at the end here, and I'm not sure if that gets us anywhere. I doubt it does, but we can check. And in terms of the normal, the get octahedral offset probably also can't really be accelerated much. So again, I don't really think there's much we're going to be able to do here. This, on the other hand, could easily have been done wide. So that may want to go. Anyway, doesn't matter. Point being, I think we're more or less there. We just probably aren't quite great yet. This is not the world's best code. For this, I am quite sure. But, you know, what are you going to do? So we really just have 2 things to do. One is we've got to figure out what the clear mask table should be. It's just a 16 entry table that we would fill with the correct mask values. It's exactly the same as like this thing here. It's just a different table, right? It's exactly the same idea. And it would just have 16 values in it. The easiest way to do this would probably be to do it this way, where we would say that these are just masks, and they're either going to be all Fs or all zeros. Right, and we would just have 16 of them. So depending on what the pattern of compares was, you would just have, 16 of these, and a bunch of them would evaluate to that, and a bunch of them would evaluate to this, right? and a bunch of them would evaluate to, this. Is that enough Fs? Yes. So that's... Oops. That's all we're talking about here. And I don't know which ones go with which slots, so we're going to have to actually figure that out. But in terms of which codes go where, so this is like, in each of these slots, we would have, a particular 16-bit value that goes in there. And this will be like the bit pattern here. Right? So it's like this. That's the bit pattern for the first one, first set. We would have the same pattern again for the next set, right? And then we would have the same pattern again for the last set. It's this whole thing repeated, right? In fact, I can just do this. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So all we would do is we just have to go then see which ones correspond here. And so if you look at how the shuffling works, and we do a comparison, we're doing XYZ versus YZX. So XYZ versus YZX means that and if it was greater, right? Because it's a greater than sign. So in here we say if XYZ is greater than YZX. So the first slot, right? Bit 0 is X greater than Y. I need a comment here. The next bit is Y greater than Z. And the final bit that we actually care about is Z greater than X. And then bit 3 is just going to be comparing like 0 with 0. And so bit 3, we should be able to guarantee that bit 3 is always 0 if we want to, because 0 can't be greater than 0. So if we want to, we could say, look, let's make this table just be, only 8 long and say this is always 0. We should be able to do that. If we can't, we can just duplicate the table, right? So it's not that big of a deal. All right. So given that we know these things, what does this actually mean? So if we have all zeros here, this means that X is not greater than Y is not greater than Z, and Z is not greater than X, right? That's what it's actually telling us. So what we know from, if we take a look at where X is being compared against things, is that actually enough? We might need bit 3, right? I don't know if that tells us everything we need. Because let's look at what we would do. Like, if we were going to write this code normally, we'd say if X is greater than Y, then we just need to know if X is greater than Z or not, right? And in the other branch, we would say if Y is greater than Z or not, I think, right? So if X is greater than Y, and X is greater than Z, then it's X, right? If X was not greater than Z, then, I guess we need one more thing, right? Then we need if Y is greater than Z. Because now we know that, No, we don't. It's just Z. So that would mean that Z is either equal to or greater than X, and we know that Y, so it's Z at that point, right? If we know that Y is actually greater than X, then if Y is greater than Z, then it's Y, otherwise it's Z, right? Am I wrong about this? I feel like that's all we would need. We don't care about tiebreakers. If two things are equal, we don't care. That means you hit a corner of a box, and we wouldn't care which normal you pick. Any normal would be fine. So I think that's fine. So yeah, so if we look at what this corresponds to, x greater than y, 0, it goes into this branch, right? So this is like bit 0 is set. And this is, right, bit 0 is 1, bit 0 is 0. I guess we could do it this way. Right? Another way to do it would just say, okay, look, 0, 0, 1. When we get in here, now we know x greater than z. So that's actually the opposite of the last one, right? That is actually important. So I think we actually want that. That's easier to produce. Probably. I think that's easier for us to produce as well. That might not be true. So we may want to do it that way because that way each vector only has 2 components. So they can be done with one shuffle potentially. So that may actually be better. All right, so in here, let's do it that way. And that way we don't have to have 3 values in each one. So if we do x greater than y, so I guess another question is, do I just do this in a simpler way that, I don't know, it still seems like it probably more instructions though, because if you don't ever make a packed value. So another thing I was thinking is like, well, actually, I mean, the other thing we could do is just do these comparisons after the shuffling. So we could do like 3 shuffles to produce XXX, YYY, ZZZ, and then just do the comparisons there. Because there's only 3 comparisons, right? Gosh, that's a pretty tough call. Because those comparisons can be done serially, right? So for example, if you've got these, you can do like this. I guess you'd have to do the absolute value a lot more times though, so it does seem like you'd want to pack it first. I don't know. I'll sketch it out first just to make sure I'm not wrong. I mean, I could be very wrong about that. But if this is all you actually wanted to do, like based on that sort of arrangement of things, you'd say, okay, I need to know this many different masks so I can figure out what, I'm actually going to put into these things. These would have to be absolute values, right? So you'd have to do an actual absolute value of each of these scaled D values here. So you'd need to produce this, and it's expensive, right? It's going to be 3 separate ands to do that. So you're looking at something like this. We have to do 3 separate shuffles, 3 separate absolute values, and then when you get down here, you do 3 separate compares, right? At that point, you would just do select to get your mask, I guess. So the X greater than Y mask is going to be all ones or all zeros. Oh, well, okay. So let's think about this for a second. So if we then do the absolute value, we now know we have 4 lanes. One of them has the correct lane, but we don't know which one yet, right? So just one of them. We haven't shuffled. If we do the comparisons, we know that now we have one lane that has the answer in it, right? It's got all zeros or all ones for each of these, and we need to merge those together to figure out which one we're actually going to use, right, in terms of whether we want the X's, the Y's, or the Z's. So what we would then do, I guess, is we'd do selects here. So I probably shouldn't have deleted that little guy. It was handy, right? So I think that's what we're talking about, right? Seems good. So if I do my X is greater than Y and I do my X is greater than Z, that's the mask for X, right? So then you would also have the not the X, Y, and not this for Z. So that's 1, 2, 3, 4. So you got 4 masks, right, that you need. It's not great, but, you know. I don't know where our other select is. It's there. So yeah, like you would then do something like this, which is, like I said, maybe not the best thing. We'll find out. So here's our masks. See how this works out. All right, so now we would need to select from one of these. So we need to produce like our X value, our Y value, and our Z value that we actually care about here. So in this case, we need to do like so, you know, if I was to do something like this, I guess it's going to select forward, so we'll do it this way. Yeah. So we need to know what the signs of these things are. So they need to have their original sign bit ORed back in as well. You can see that this is probably just a lot slower to do it this whole way. Right? I mean, it seems like it. I don't know what you folks think, but it seems like sketching that out, this is just the way I was saying to do it before is just better. Right? I mean, it seems like if you did it this way, you're just doing a lot more work if you don't compare it while packed, because you don't really have to do a lot of unpacking. So I think this is just worse. I think it's just worse. So I would say, like, okay, let's suppose we want to do what we were going to do up here, where we had, so the XYX thing. So the only problem with that too is that, like, we kind of want the XYZ because that's the actual thing we need to use later. You know what I mean? So it kind of seems like maybe, I don't know, like although doing it this way seems, I mean, you can just do it this way and have it be not, you know, have it not be exactly the same pattern as the ifs in here, because you can just swap these around. Like if what you have is XYZ and YZX, then when you actually get to the point where you need to do the X greater than Z, you can just do Z greater than X and put the Z, you know, here and the X there, right? So we can do it either way and keep an XYZ. And the reason that I'm saying that I think I want that, because it would be nice if you only had to do 2 for each, but we need these packed later to do the store, presumably. Now, maybe you don't. Maybe you could do it in a slightly cleverer way, but it seems like we need that, so let's keep it this way. So when we then go to do our table, this is our clear mask table. I also think, do we have a sign bit? We probably have a sign bit value somewhere here, but we'll make one. So if we have to load out of our clear mask table here, what we want to do is just track what these values are. So in this case, we know that the first bit would be 1. In this case, the first bit would be 0. When we get in here, this would be the first bit is 1. The second bit is, and I guess I'll do it this way, right? The second bit is Y greater than Z, so we don't know what that is, but we know that the Z greater than X bit, the other bit, is also 1, and then this should always be 0. Like, we know that that value is always 0, right? So we'll basically do this, or maybe this, right? And then in here, we have the opposite. So that's this. So we just don't know what that middle bit is. You know what I mean? It could be anything because we don't know how Y compares to Z. So in here, we have a similar situation, but it's blank, blank, 0. And so then what we have is for the Y case in here, we know that Y is greater than Z. So it's who knows 1, 0. In this case, it's who knows 0, 0. Right? So then if we look up what those correspond to here, if we look, we know that blank, blank, 1 is, 1 blank 1 is here and here, right? And so 1 blank 1 has to produce Z, which would be this. And the same would be true here. So any pattern that's 1 blank 1 has to produce Z. Any pattern that's 0 blank 1 has to produce X, right? So 0 blank 1, 0 blank 1. And those already did produce X. That just happens to be what we wrote down the table. Anything that produces blank 1, 0 has to be Y. So blank 1, 0 has to be Y. Blank 1, 0. Right? Anything that ends in 10 has to be Y. And then finally, anything that's blank 0, 0, so this and this, that has to be Z. All right, that is not Y. I wrote Y, but I didn't do Y. There we go. So we've got 2 cases for X, 2 cases for Y, and then everything else is Z, because those are the else clauses, right? If we're not sure what's going to happen with the high bit and we want to ensure we don't read off the table, we can just duplicate this, right? So we can do this if we want to. And that ensures that no matter what happens with that comparison, we'll still get the same values. In this particular case, you can also see the effects of this. So this is 16 bytes. So every 4 of these is a cache line, right? So it's also free to duplicate the table. Because it doesn't cost us anything, right? It's free. We don't care what those values are. They're never going to get used, or they are. If we don't, so we can make the table be this big, and it doesn't cost us anything to do so. And then we want to try and look up only into the bottom part, because that obviously saves us a cache line, 2 cache lines. But we don't actually need to do that. So if we have a situation where it's massively faster not to for some reason, then we could just avoid it, right? But it seems like we would really want to not do that, because we don't want to have to look up into a second half of the table. So we don't really need that, but we can stick it in there for now just to eliminate a possible source of error, and then later, if we make sure everything's working correctly, we should be fine. This is probably just that. And now we just have to actually pack this stuff together properly. So there's a couple things. One is that we need some way of actually loading out like this we haven't written. The other is we just need to actually produce these values here, right? So we need some way of doing the shuffles and all that stuff. I thought we wrote a shuffle of one kind or another here. Here's a shuffle 4x, right? So I think that is just all we need. Absolute value already exists. So absolute value is here. So there you go. And so the sign bit here, right, we should probably just, oh, and in fact, you can see it. It actually does sign bit from is a thing. So we can just do sign bit from this on the inside. And then we're down to literally just these two, right? So let's start here. The clear mask table loading out a clear mask here. The problem with that is we actually need this to load as if it were as if it were an MM128, right? So we need this to be an M load UPS, like so, right? And I don't know what it's complaining about. Tell me again. Cannot convert from F32X to M120. What? Oh, sorry. Is this a... Do we have this in here? Yeah. So it's that, because we have our own type there, right? So we can do a load. I don't know if we have a mask extract. We should really clean this stuff up, because we could do this all with our own types and it would be fine. But I don't know if we actually have that. It doesn't look like we do. So we probably need to like add that, like a thing to move the mask out, but whatever. All right, so if we take a look at what's left, here's our load. I don't know what's the problem now. This is comp.p. So really, we're just looking at a few last little things here. Probe n, this is actually probe n single 3. So let's just get rid of that. All right. So now we just have to do the packing and the unaligned copy, right? And that's just to get this thing out into something that the rest of the code can use. So when we want to do this packing, I'm assuming this is literally just going to be some of these. So if we do packed XYZ, we would first need to do a shuffle where we have the scale D here. And what we would want to do, I guess, is say, well, let's start by producing an XY vector. We'd probably have to use the shuffler here as well. So this is probably like... So we're probably not going to get away with anything other than doing that. If we produce the XY vector here, this would just be like, okay, you know, it's just... So that would be XXYY, which is not really what we want. So this is probably not right. What we probably want is unpack. I hate these intrinsics. They're so obtuse. Hold on a second. Well, it's the instructions that are obtuse, to be fair. Okay, so it's unpack low PS is what we would want. And so that'll give us XY, XY, right? And then we just want the Z value to come in at the end. So then we would just do like shuffle 4X. With the packed XYZ, taking the bottom two as you'd expect, and then the Z value up on top just comes from scale.z, right? And we don't care what it puts in there. You know what I'm saying? So that actually will have a Z value on top of it. When we do the shuffle here, let's think about this. So to produce YZX from XYZ, we want YZ, and then we want to produce X. And the final value, since this is ZZ, if we want to do Z is never greater than Z, right? What we would want to do is take the Z again. So I think that means we can just say verify that bit 4 is always 0, or I should say bit 3 is always 0, and then remove this half of the table. So I think that's okay, right? And I think that gives us everything that we need there. And I don't know that we don't really have one of those, so it's unfortunate, but whatever. So the last thing that we need to do is a way to actually store this out. Let me just see what we've got for that already, because we probably have a store U. Yeah, so it's this. So it's really just that. We're going to take this value and we're going to stick it into the slot that we made for it there. It's probe and single 4. And then I think we're good. So again, not the world's greatest routine. It's pretty ugly. But if you actually look at the number of instructions, it's not horrible. Could we probably get that down by, even possibly get it down to about half the instructions? If we really ground on this, probably. Honestly, we probably could. Do we care? Probably not, because it's going to be still, I think, be quite small compared to the other way this is happening. The number of ops this has to do is probably still going to be quite a bit more. But we don't know that for sure, so we probably should grind on that at some point and try to clean it up to as clean as it possibly can be. But I think we're good now in terms of actually having grid raycast produce reasonable values. Now, the problem we're going to have now is we need the actual tables that this uses. So the grid ray cast routine needs to actually have this stuff in it. And if we look at how this is set up, we need, so in here, for example, these tables like the lighting spatial grid node and the lighting spatial grid leaf, these things all now have to actually be set up, right? So we need all of these things to get generated somehow, and we don't have a way of doing that yet. So that's one thing we have to do. And then the other thing we have to do is this walk table here, where we're going to load up what the actual leaves are that we walk along. That's also something that we have to do. That table is a known table. So it's a table that we just have, like when we actually have our HH sphere code here that generates the spheres. Each one of these is something that can now also output one of these walk tables. So we will be able to get the walk table just out of the spheres themselves. And if we look at like what HH sphere is generating, so if we look, for example, in here where it's doing these light sampling sphere float tables, this thing. So when we do a light sampling sphere, in addition to the sample direction thing that it will have here, it would also have a way of looking up the walk tables for those directions. So much the same way as it has light sampling ray bundles per sphere. Also, what is this padding for? I have no idea why there is padding in here. I do not know what the point of that is. So that is beyond me. So anyway, you're going to load up the sample direction here, and then you also need another piece of information, which is the padding for, the walk table for these things. So what we probably would want to do, because like I said, we're not casting 4 rays at a time anymore if we do this, we would probably want to make a separate kind of table, and that table would actually be a different type of structure. So in here, it's like light sample direction. It would have in it the direction, the count, and the offset. So you basically load these up, and they tell you like where in the walk table you're looking and what the actual thing is. So you'd load, this would literally be, one 16-byte value that has 3 floats for the direction and an offset and a count for the walk. This count is not going to be actual 16 bits. It's more like this. Right? So it's hard to say exactly, do you need anything else in there? I'm not sure, but the walk offset would have to be 16 bits because there's going to be probably more than 256 entries into this table. But there you go. So what you would actually be doing is when you call grid raycast, you'd actually just be giving it this instead, would be my guess. So rather than any of this stuff, you would probably do something more like this. Like that. And then you would produce these other values. Oops. You would produce these other values synthetically by like unpacking. So you would say the ray D single is the sample direction, or this would actually be like the ray D, because this whole thing is now the information about the direction. So the ray D single is just the ray D that comes out of the sample direction. The walk count is just the sample directions walk count, so you're just pulling that out. And then the walk table that you're looking in is just whatever the sample direction walk offset is off of the solutions walk table, right? And I think that's it. These are constants, actually. So you don't actually need this. So that's probably, honestly, just a global table that you're walking through. And I don't think you need anything else. Yeah. All right. So I think that's all you would need to do. The walk table here is just a series of lookups. So this would be like a global U16 light sampling walk table, and you'd just be looking up in there. And it's who knows what this value is, right? It's something. We don't know what it is. And then this routine would just operate if it had this information. I think that's what we want. Looks right to me. Yeah. So I'm relatively happy with that. I think that's pretty good. I don't actually know. I don't actually know instinctively how well we've done here. Maybe quite poor. Maybe not. I'm not sure. This part looks very good. I mean, I could be wrong about that assessment, but this part looks really good. You've got like one shuffle. That's just a shuffle. So that's like one instruction. You've got another instruction, another instruction, another instruction. So you're talking about 4 instructions, maybe latency like what, like 6? Maybe 7 cycles to downshift to know like, okay, now we have something that can produce the correct lane out of anything we want. So that part seems pretty good. I don't know how much better you're realistically going to ever get there. I mean, 7 cycles is pretty darn low. So I think mostly we're talking about this part here as being the questionable part. And the bottom half looks fine. The top half, like getting that normal just looks really expensive, you know? So here's some thoughts, because I guess I'd probably like to save writing the table stuff for tomorrow. Let's just think about this normal computation a little bit more. As the tangle of chords on my desk grows more and more absurd. So if we were to go here and I was to sort of blather on about this particular problem, what I would say is like, okay, you know, I know a lot of things about this answer. How many of them can I use? So if we imagine here is our axis system, like so. Uh, what I know about this is if you imagine whatever the ray direction is, so there's a ray direction and it's pointing in some way. The normal is always going to have the same sign as minus the ray direction because it can't not, right? So the normal, whichever one it is, when we look here, it can only be one of these things. So if the ray is coming in at like, in this case, what is it? It's negative z, positive x, right? Negative y. Then we know that the normal has to be the opposite of that. It has to be this sign, right? So negative something could be 0, but it's negative something, positive something, even if it's negative 0. And that's true, right? Because this would be positive x, right? Wait, how did I write positive x? This is going... Wow. Slow morning. This is going the other way. It's going negative x, negative y, negative z. So it's all positive, right? And that is exactly what you see, right? Those are the only 3 normals you could hit. You can't hit these sides because they're back facing, right? So we know the sign is just whatever the flipped bits of the ray direction were. So we can compute those directly. So then the only thing we need is to mask out. We just need to produce something that masks out 2 of these things. So we would do, if we had the value 1, 1, 1, we can produce the correct signs by ORing in the sign, by ORing in the inverse sign bit. So we would not and then OR. So like, not OR gives us the sign bit. So that's 2 instructions for the sign bit, right? But 2 instructions per channel because there's X, Y, and Z channels. We could pack them, I guess. And maybe we want to. I don't know. So we pack those. Maybe we pack those first. Then we do the sign. Oh, and it's free to pack them because we need them to be separated. Well, I don't know that we actually do need them to be separated. At the moment, for compute voxel, we do separate them. So hard to say, but something like 2 instructions for that. And so we're just looking for a good, cheap way to produce the mask that is basically like, then we need to do an AND here to knock out 2 of these, right? So we need to knock out 2 of the normals somehow, 2 of the components. And in order to knock that out, we really kind of, that's where we really start to fall down. Because that's why we're having to compute, like, the difference between these 2, which is what we were doing before. And then we had to figure out, like, well, okay, we need to normalize that by the box radius in order to figure out which ones we should get rid of. So is there some better way to do it? Yeah, I don't know. So one thing I will say is that it would have been we could have gotten rid of these P-Shuff Bs if it weren't for the fact that the hitbox min and max are not P-Shuffed, right? Uh So here's another question. Are we thinking about this at the wrong point in the code? So one of the things you can see here is what we do is we keep the box min and the box max, right? But if we look at what we actually determined here, one of the things that you can see is the tmin3 and the tmax3. That was previously keeping. So we know, like, we've done a comparison here and we know we've picked a particular t value, right? So we know whether we've hit like I'm just trying to look at this through. You can see us loading the min and max in, right? And then we take the box min and max and we multiply by that inverse radius dimension to see when we would hit the mins and the maxes of these boxes. So maybe if we just saved some of that instead, we could extract the normal directly. Because the tmin and the tmax value are telling us the answer, in a sense, right? When we produce these two, we're saving, when we produce this tmin and this tmax, we're producing them by comparing the x, the y, and the z and taking whichever one is maximum. But whichever one of those was maximum is the answer as to who was the normal, right? And these are expensive. I mean, storing this is expensive. So it seems like what maybe we could do is just say, what if we don't store this? Like, that's just not something we keep. And we do like a mask extract on one of these. This feels like the right solution. It's just kind of hard in my head to understand what's happening. But I think this will be better. Because that is 6 select operations, right? Which, by the way, don't have to be done this way anymore. We can do this in 1 instruction instead of 3 instructions. But even so, it's 6 instructions here, and they don't pipeline. They're all on port 5, if I remember correctly. Like, basically, shuffles are always port 5. Or blends, or is that not? No, wait, that might not be true. Let me see. Nope. I take it back. So they do stack. All right, so hard to say. So those are pretty cheap. So it's only like 2 instructions. So I guess it would be pretty hard for us to do, unless we were really clever, it'd be pretty hard for us to do. We'd have to do it in 2 instructions in order to not suck. So how do we do that? How do we do that? The tmin3.x, tmin3.y, tmin3.z, where we pick one of those out. Yeah, I don't know. I mean, fundamentally, we just need some way of figuring out which one we picked, but we've filtered the values down to get whichever one is the actual hit, but we don't actually know which one we picked, right? If we knew throughout these we're just keeping the minimum value. If we knew throughout these operations which one we'd actually taken, that would do it, but we don't. However, maybe that's not true. Okay. I think I've got it. This may be me going totally nuts here, but hear me out. Previously, we were storing 6 values. That means if we store any less than 6 values, or anywhere up to 6 values, we haven't taken a loss. Suppose we were to store tmin well, and actually also, if we look here, we only take tmin. So T inside, we don't use. So if you're inside something casting out, we ignore it, right? In other words, this is not used anymore. That was only for boxes that were like container boxes. So we don't need T inside anymore. So we're only taking the T min value. Right? So T max is only there as a check for collision. We never record that value. We will only record T min, right? We're actually questioning that as well. Like maybe we don't actually need that. But I don't know. We'll leave that because we don't really care about that for now. It's 1, 2 ops, whatever. We'll look at that later. So what I would say is I think we can do this. Since we only record T min, we can instead do hit hit T min and hit T min X and Y, right? So we could do this. And what we would do is just store, when we had done those comparisons, just remember what these were. Right? So we're just, like, all we're doing there is remembering those two values using two instructions. Two blend instructions. Right? So it's super, super, super cheap. We could recalculate them at the end even if we wanted to, I suppose, by just store it. But then we'd have to store the box. So, yeah. So, right? I mean, I think that's... super cheap. So we're storing way less there. We're just storing just what the T min X and the T min Y are. At that point, at the end, when we get to here, we would say, we don't need any of this. We don't need this. We don't need that. Or any of this. We need none of that. All we actually have to do is just take our hit T min and hit T max. Hit T min X and hit T min Y. And we know that one of these X, Y, or Z will be equal to the actual answer that we got, right? So, in other words, when we found a minimum T value, we know that it was either the X, the Y, or the Z. So at that point, we should be able to say, well, whatever our T-ray was, because our T-ray has already been shuffled up here, we should be able to say, well, figure out which one it was. Because either it's going to be hit T min X, hit T min Y, or neither of the two, in which case it was Z. Right? We already know the sign, because the sign comes from whatever the direction of the ray was. Right? So if we extract the sign bit from whatever the ray direction is, it's the opposite sign of this. That's all we needed to know, right? It's whatever the opposite sign of the ray direction was. Now, we would need to pack the ray direction, so we'd still need to do this. But otherwise, it's correct. And if we wanted to keep all this wide, we could. None of this is necessary now, I don't think. Pretty sure. I don't think we need any of this. Oops. So we can get the sign bit out of here, and we can do that. I don't know exactly which ways we want to do that. I mean, you can sort of see it's a little bit of a mess. It depends on how you want to leave it. But, you know, we can either keep it wide or we can collapse it down, and I really just don't know which one makes the most sense. I feel like maybe just keeping everything wide, because as soon as you then start operating with them again, they need to be wide anyway and blown out into different registers. So it may be that all of the collapsing down is just a fool's errand, and that you should just have compute voxel radiance at take wide in. That's probably true. We'll look at that a little bit later. So let's see what goes on here. So if probe sample P is computed, that's all done already. So ray D is the only thing we would need. And so let's just do it wide. We would have ray dx, right? Ray dy and ray dz. The sign bits here need to be knotted, so they need to be the opposite of what they are, right? So you would need to take like the inverse sign bit. Like from here, where we're doing sign bit from, you can see here like it's knocking out whatever the other value was there. So we also need to do an XOR with this. So we would want to do, you know, like inverse sign bit from or something like that. And in here, what we would do is say, well, we load the mask, right? We AND with the mask, and then we XOR with the mask to flip it. Right? So I think that's right. Like that would like toggle a bit. So basically like you've got ones in the high bit. So anywhere there was a 1, it'll become a 0. Anywhere it's a 0, it'll become a 1. You got zeros everywhere else. So then everywhere that there were zeros, they would stay 0. And everywhere there were 1s, they would stay 1s. I think that works. So here we would just say, all right, get the inverse sign bit from each of these. There's our sign. That's the sign of the final result. So we now know exactly what the sign is. And so now the only question is, what's the mask? So, you know, if you took the normal, you now have basically this. I don't know how we want to produce this, but it's like written out. So the sign bit gets ORed in, and we just need to know in each case, do we pick a 1 or a 0, right? So you're basically just, you know, you're doing like this, a select, but since you know one of the answers, since you know that you're either picking 0 or 1, we should just be able to just do a straight AND. We don't really need to do a blend, right? So this is just like 1 AND mask in each case. Right? So okay. So now we're getting somewhere. This is way, way better than it was, unless I'm on total LSD trip here, and it's not actually correct. So doing it this way, where we've got normals and we just need to now know the masks, the question is, what are these three masks, right? So there's an X mask, a Y mask, and a Z mask. So we just need to figure out what those are. Well, we know which ones we picked. Did we, right? Because we've got this. So we can just compare T-ray in each case. So we can say, look, the mask for each of these, the X mask is going to be if these things were equal, right? The Y mask is going to be if these things were equal. And maybe we need to make sure that we have not the X mask knotted off here as well. So it's a little bit hard to say, but yeah. So we just say, look, is it equal to T-ray in each of these cases? And this has to be p-shuffled by the shuffler in order to make sure that we get the same answer in all four lanes, right? If we knew that we could never have the same T-min in both places, because that would produce a normal that kind of like gives us the diagonal normal, which is actually right, but we don't want to have to deal with it. Like, we don't want to have to normalize the normal after this. Like, that's just wasted work for the case where you happen to hit exactly on the vertex, you know? So this is going to be X or Y knotted, right? Which I don't know that we have. Yeah, we don't. So I don't know if we have and not. We do. So actually, that's not true. There you go. So yeah. Right? Like, holy cow, is that better? Way, way, way less instructions than the old version. Way less complicated. And I think it does the right thing. We know the sign because the sign always has to point in the opposite direction. Right? In theory, we could even put that into the mask, maybe? I'm trying to think. I think that's fine. So I think that's just fine. I think that's just it. Yeah. So I want to say that's grid raycast, right? I want to say that's the whole thing now. And boy, is that simple compared to what it was before, right? That's like way, way better. And so when we're doing compute voxel irradiance at here, how much time do I have left? I don't know how much time I have left. Probably only 5 minutes. When we're doing compute voxel irradiance at, we just wouldn't, like, we would just change this to take the non-downshifted lanes. And then it would just do these ops on F32s, F32 4Xs, right? So I think that's it. I'm pretty happy about that. That's like way, way, way better than it was. That's probably how we should have been doing it before. And you wouldn't call P shift B in the other case, right? So this is probably how we should have been doing it the whole time. Like, that's, like, not a little bit better. That's, like, radically better. That's, like, so much better than the previous one. Even just in terms of legibility, it's better. Let alone the fact that it's so many fewer, like, gyrations and there's no tables or anything, so you don't even have to worry about loads and things happening in there. It's like 1, 2, 3, well, maybe 4, let's say 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 instructions. And that's it. And you could probably get it down a little bit more. This is probably not as clever as it could be. Excuse me. Like, we probably could do something slightly clever as well. But all right. So let's just finish up the piping here. So we need these, like, when we do grid raycast, we need to pass, like, this thing. And so there would be 4 of these that would be happening in here as well. And so right now we're just going to pass nothings to those. And so in here, rather than any of these things, we'll deal with these a little bit later. So this is just this. And that's what we'll have to be generating in our table. All right. Yeah. So we can also run this right now, and theoretically it should not crash, but it won't do anything because there's nothing in those tables, right? So it won't actually tell us anything. It's meaningless, but we can run it anyway. Right. And hey, like, it's also, like, crazy fast because it's not doing anything. Like, it's not actually testing. So you're only, like, what you're seeing there is the total runtime cost for the, like, really expensive diffuse blur, which is actually kind of a great thing to see. Now we kind of know, like, it's 2.3 seconds in our test bed for doing, excuse me, for doing just the downset, the blur, the specular to diffuse. All right, let's go ahead and go to Q/A. Nice upgrade of the routine. Just want to let you know there's a double P shift in the creation of T-Ray single. Oh, really? That was not my intention. I've kind of worked over this routine a few times here, so we haven't really had a chance to go through it and make sure that there's nothing stupid happening. You are correct, sir. That is not even remotely necessary. As for what it stands for, it's actually, the P doesn't stand for anything specific to this instruction. The instruction is really shuff B, which is shuffle bytes, I believe, because it's a byte-wise shuffle. The P is actually the prefix that they chose when they were assigning this the SSE instruction mnemonics. The P just stood for packed. So what you will see if you actually go look at the instruction breakdown, the way that it works is like when you have, for example, like, so let's say we were just talking about the early days. So you only have like SSE, MMX, and the base stuff. I mean, MMX would have been the real early days. In fact, actually, we could probably do that with just MMX. So let's suppose you looked for like add instructions, right? And I think you could just, I haven't looked in a long time. Yeah, you can. So you have to imagine like you're coming from x86. This is before x64. And you've got, you've got your add instructions that the processor has. So the x86 add instruction, it looks like this. Here's an 8-bit add, right? You add one register to an immediate in this case, right? Here's an 8-bit immediate and add, right? 2 register adds. Here's a 16-bit memory to 16-bit register add. So that's your add instructions. They're called add, right? When you get to MMX, which MMX is the first time that Intel had wide instructions, so more than one thing could happen. Like inside a single register, there could be more than one value being added at once. So there's boundaries in between them now. You can see that the multimedia registers here that they're talking about, like the MMX registers, suddenly you get a P in front of it, right? And the P now stands for packed. So packed add bytes, packed add D words, doubles. I don't know what the D was here. I don't remember all of their mnemonics. This is saturating words, saturating bytes, I believe, right? Saturated versus unsaturated. An unsaturated add is an add that wraps around. You add 1 to the highest value, you get the lowest value and start again. Right, so it wraps. Saturating adds, they go to the highest value and stop. So if you take the highest value and add 1 to it, it remains the highest value, right? And so originally in x86, there's no such thing as a saturating add. You can look through all of the old x86 instructions. There is no such thing as a saturating add. Adds always wrap round. But in when they started doing multimedia instructions, they wanted to have it so that like if you added 2 color values together that would have overflowed 8 bits, that they saturated. Why? Because they didn't have any extra room. Normally nowadays, we always do computation with headroom. So if you're going to do 8-bit computations, you do them in 16 bits so that you have room and you can do something with the values when they overflow. The saturating adds were an attempt to make it so that you could do stuff on values where you didn't have any extra room, right? Because this was the early days. You didn't have much extra bandwidth. You're trying to get every last bit to count, right? So P-SHUF-B just follows that naming construction. If we switch back to SSE instructions here, and we look at P-SHUF-B, what you can see is all it's saying is it's packed. That's what the P stands for. SHUF stands for shuffle, and B is the identifier for 8-bit values, so bytes, right? If you were going to shuffle something that was different than that, so if you were going to shuffle, say, 32-bit values or 16-bit values, you'd see like SHUF W for word, which was like if they had a SHUF, I don't even know if they do. Yeah, so SHUF W's are all here, but since they only work on half the side of the value usually, it's high words, low words, right? Etc. Hopefully that helps. Hi, Casey. Love your show. Lately, you seem to be having some problems with your voice breaking, coughing. Have you considered visiting a speech therapist? I probably should, but nowadays probably not something I'm going to be doing, right? Oh, Miblo says the episode guide has been updated. Is this true, Miblo? Oh. Interesting. Oh, look at that. It's got all the different sets in here now, too. That's kind of cool. Haha. That's cool, Miblo. I'll have to check out all the new additions to it.
Okay. So what you have to remember.
That's great.
And I
Nice work, man. Could you explain the math diagram behind why the sign bits are the inverse of the raised sign again? I showed up halfway through that and I think I'm missing some context. Sure. All right. So let's suppose I have two planes, right? If you've never watched Behind the Curve on Netflix, you might want to check it out. It's about the people who are trying to advance flat Earth theory as a alternative to the scientific explanation that the Earth is a roughly spherical shape, which is interesting because one of the odd things about flat Earth theory is we don't really care what shape the Earth is anymore in that way. Like, in the old days, when you were wondering what would happen if you sailed too far in one direction, then what shape the Earth is the way you're thinking about geometry. You're like, does it like wrap around, or do we just hit like a wall and there's like nothing after it, or there's a totally different world after it? Like, what happens, you know? But like nowadays we're struggling with things like, okay, so we know topologically what happens when we explore the Earth because we did it, right? And furthermore, we also know what happens observationally when we're outside the Earth looking back at it because we did that too. But what we don't know is like, what is the actual like physical structure of the universe? Right? Like we're struggling with that. We don't know. But flat Earth, like the shape of the Earth, that's not what we're trying to think about, right? Like, they're still trying to solve a problem whose solution doesn't actually tell us anything. Like, I guess because people who are flat Earth theorists don't know about like space-time and the other stuff, like they aren't able, I guess, to conceptualize the kind of harder problems that we're now facing. They think that somehow if someone was going to have a conspiracy theory and lie about something, it would be that. But that's like so far back in the conceptual realm that no one would bother to lie about that, right? Like, that's not, if the Knights Templar and the Freemasons and everyone else got together to like lie to society at large about critical elements of how the universe works, the shape of the Earth is so far back on the list of things that you wouldn't even bother lying about that anymore, because there's so many things that we now do that make that question irrelevant that you'd be lying about space-time, right? So it's kind of funny to watch people construct a conspiracy theory around something that would not be something an all-knowing, all-powerful force would ever want to lie about at this point, because we don't think about that anymore. Like, we don't use that knowledge anymore at all. We use way more advanced stuff that just that is a thing that falls out of it. So if you were going to start doing, if your core goal at this point, if you were really actually very smart, like you're Stephen Wolfram and you're going to develop a new kind of science, you need to start way further up and then demonstrate that, oh, by the way, that also means the Earth is flat, but like that's, you know, just a thing that falls out of the actual space-time equations that we now are telling you to use, which happen to end up, you know, anyway. So let's suppose that the Earth is flat, of course, and when the Freemasons built the fake display system that shows our heavens to us, you know, it was this infinite flat plane, right? That's above us and just very, very large. So let's suppose we are the Freemasons, so we're the only people, or the Knights Templar, or whoever else the people are that are the CIA. So out here in the place outside, like, you know, this is poor Earth, right? Oops, sorry, I drew it as a sphere, my bad. So Earth is in here, and of course it's flat. And so there are these planes that we're keeping Earth people ignorant by displaying fake heavens and stuff on them. And then the CIA, Freemasons, Knights Templar, whoever else, depending on how racist you are, there's probably other people in there. I don't even know. But the horrible groups that are keeping us from knowing the truth about things, they can get outside it, right? So they can get outside this fake thing. So if they want to then look in on this system, then if you assume that there were, I mean, I don't know, if the Earth is flat, then in theory you could maybe walk around to the other side and see out. We would need, maybe just for insurance purposes, if there's intrepid explorers, we would need, you know, 2 infinite planes, one on either side. So when the CIA in their orbital mind control laser satellite is out here somewhere looking in on the system that they built, then when you think about which of these 2 planes they're going to hit first, what we could say is the plane that's facing this way versus the plane that's facing this way. So we're thinking about like all the gears and machinery. We're looking at those, right? The lovely display surface that the Earth people sees on this side. What we know is that whichever side of this we're on, if we actually ever hit this plane, meaning we're not pointing off in the opposite direction, if we were ever actually able to hit one of these 2 planes, we know we can only ever hit the plane whose normal was pointing back at us, right? Because if we were here, by the time we got to the plane whose normal is pointing the same direction as us, we would have hit the other plane first, right? We would have hit this one. So we can't ever get to this one because this infinite plane would have stopped us, right? So how does that translate into a box? Well, a box is just a bunch of infinite planes, right? In 2D, it's 2 sets of 2 infinite planes. This set here and this set here. Wherever we are, right, you can see that this forms 4 quadrants. Wherever we are, in order to get to whichever pair, in order to get to the one in each pair that is first, we know that we can never hit the corresponding one first. So if I was going to hit this plane first, whichever vertical plane I'm looking at, I know I'm going to be hitting the one first whose normal points back at me, right? Whichever it is. And if I was pointing in the same direction as that, I'd never hit it. I'd just walk off into the distance, right? I will hit it negative, but of course we clamp t values to 0 in the raycaster, so you can't ever get there. Same is true of this pair. I can't ever hit the one that's pointing the same direction as me because I'll hit the other one first. Will I hit this one eventually? Sure. Will it be the earliest one? No. Right? So what we end up learning is that for any given box, no matter how many dimensions I draw it, it is made up of pairs of planes, and no matter how I try to aim at this thing, if I will hit one of the planes, it will always be the one who's pointing towards me, not pointing away from me. As a result, the sign of this must always be the opposite of the sign of this. Right? Whichever one I hit will be pointing back towards me. I'm pointing one way, it's pointing the other way in all pairs of dimensions, right? Or in all dimensional pairs. And that's true of any dimensional shape, right? So when you are constructing your flat Earth theory, and I'm sure all of you out there are, because now you know that the Earth is flat and certainly not round, that would be absurd. That's just something you can take to the bank. In the n-dimensional flat Earth that we all know is true, you can tell all your flat Earth friends that the CIA, Freemasons, and Knight Templar, when they're floating outside it, will always see the one of the two infinite planes that they are has its normal pointing back at them, not the other one, because they can't actually see through it. I'm assuming there's like a door here that the CIA goes through or whatever, that like, I don't know, maybe like during an eclipse, like the CIA like goes in and out of that door or something. I'm not sure. It forms 9 quadrants, not 4 quadrants. Oh, I see what you're saying. You're just talking about these other ones here. Well, these aren't really necessary. I mean, is the way you could think about it. Meaning, whether or not we hit this plane or this plane is only based on whether we're here or here. Right? It doesn't matter. Maybe to make this a little bit more concrete, suppose we're here. If we're here, we can't hit one of these planes first anyway, because we'd hit this one, right? So it literally doesn't matter which one we shoot at when we get to here. Probably should have said that, I'm sorry. I was just thinking about cases where you could actually hit this part of the box, right? So in the 9 quadrants, if you're in any of these parts are just fully deterministic already. If you are in any of these 4 quadrants here, or they're quadrants because there's 4, but they're actually part of a octant, I guess. If you're in one of these 4 of the octants, then you know immediately what your normal is. It's just this, right? When you're in this octant, any of the 4 corner ones, you can hit either of these 2, right? So when you're in a corner octant, those are actually the cases we are trying to handle. If you could only ever be in these 4, we would have a much easier job, because then you know exactly what your normal is, just by the quadrant, right? Because there's no ray. A ray that tried to hit either of these 2 planes would miss the box entirely, right? So. this doesn't have really anything to do with anything other than just the fact that we know it has to be pointing in the opposite direction. Even if this were not axis aligned, you could just transform it so it was, right? But the property still holds even if you aren't axis aligned. It's a dot product equation now, right? So instead of signs, because the reason that happens is because when you are axis aligned, right, sign equals dot product, right? So the inner product and the sign are the same quantity, which is not true. Shouldn't say quantity. Let me explain the whole thing. If you have axis aligned vectors, so I have a vector that's like 1, 0, 0, right? If I have axis aligned vectors and I do an inner product, then the sign here, right, positive or negative here, translates directly into the positive or negative of the dot product. You know what I'm saying? Because these cannot contribute. So whatever the sign is here, right, because the dot product is, ax, bx plus ay, by plus az, bz, right? If you know a priori that you don't have two of your terms, then the sign of this is what translates directly into the sign of this. So these two signs, whatever the sign of ax is and bx, those produce my answer. I don't need to know anything about the other values at all, right? So if I know that a is, plus or minus 1, and I know that ay is 0 and az is 0, then all I'm doing is I'm saying, okay, the dot product will be completely determined by the sign and value of bx, and then I will either flip it or not based on ax. And that's the whole dot product, right? So now if I say, well, I want to do dot products with many of these, like I want to do a dot product with plus or minus 1, 0, 0, 0 plus or minus 1, 0, and 0, 0 plus or minus 1, right? So now I've got, all of the so those are all the vectors that are normals on this thing, right? Here, 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 right? So if I do dot products with all of these vectors, right, then I know which side of each of these things you're on, right? I know which side of this you're on, I know which side of this you're on, I know which side of this you're on, and so on, right? Now, in order to actually do the side, I need to take the vector relative to this. So I'd have to actually see what you were relative to a point on the plane, for sure, but you get the idea. If I was to construct the same algorithm, but things had to be spun, so here's the axis system, but now my box is like this, you could still do similar things, but you'd have to actually take the dot products, right? You couldn't cheat and just look at signs anymore. So one of the reasons we like to rotate things into an axis-aligned space, or just construct the algorithms in an axis-aligned space to begin with, if we can, if we're lucky, which in this case we can, is because all of these dot products degenerate down into just signs. You're either changing or not the sign of a value, right? Bx is coming in as a real value from negative whatever to positive whatever, right? That's a real value. But the only thing your dot product is doing is plus or minus. It's just changing the sign. Either we flip the sign or leave the sign the same. And so you can drastically optimize operations that used to be whole dot products doing dot products of things by just using sign flipping or sign overwriting. And that's what we did here. Right? Is it faster to do the matrix rotation or the dot product, though? I guess there's only one rotation in plane of dot products. So if you're in a situation like we are, where all of our boxes are axis aligned anyway, then obviously it's free because now you don't need to do a rotation. If you're in a situation where you're not that way, so you have rotated boxes and then you want to do it, then whether or not the rotation is cheaper or not depends on the algorithm. It may be cheaper to just construct it with the dot products. It may be cheaper to do one rotation first to put it into an organized coordinate system and then do it. So it's really just a case of looking at what the algorithm does and seeing which one makes more of the operations, makes more instructions, and which one makes less. So, all right. I think that's the end of the cues. Oh wait, no, there's one more. If you're curious about sign distance fields, I literally just did a Q&A on sign distance fields like literally like 2 weeks ago. It was a question. Did we not get this? I mean, here's another one. But I thought there was more. Might have been in the pre-stream. Might have been the pre-stream. You missed it. Should have been here. All right, I'm wrapping it up. It might still be in the Twitch VODs. I don't know. Those don't get annotated. All right. Thank you, everyone, for joining me for the episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow the series at home, you can always go to handmadehero.org and pre-order the game. It comes with the source code, so you can follow along with it. We also have a Kickstarter that it now has probably less than 24 hours left. If you would like to get our comic, Meow the Infinite, now is the time. I guess you got 23 hours left. You can go check that out. It's got a cool trailer. That will be running for another 24 hours, so by the time I'm back here tomorrow, it will be over. Well, I guess it'll be during the stream that it'll be over. So do check that out if you're interested. That's it for today. I'll be back here tomorrow when I will look at implementing the lookup tables we need so that we can actually start testing this routine, which will be a lot of debugging, but hopefully we'll end up with something significantly faster. We'll see. We don't really know. That's it for today. See everyone tomorrow. Take it easy, everybody.